In this video, we will look more at the exponential function and its derivatives. Suppose we have y equal to e to the power of f of x. Then from the chain rule we know that the derivative will be f derivative times e to the power of f. Let's look at an interesting property of this result. Again, suppose we have y equals e to the power of f of x. The derivative will be f derivative times e to the power of f. When will the derivative be 0? Well, that will be when f derivative times ef equals 0. However, the function e to the power of f of x is never 0, and we can cancel this out. So, we simply get the result that y equals e to the power of f of x will have derivative equal to 0 when the derivative of the power is 0. Let's look at some examples. Where is the stationary points for the function e to the power of 1/3 x cubed plus x squared plus x minus 1? The derivative here requires us to differentiate the power and bring it down. So the derivative of the power times the original function. The derivative of the power in this case will be x squared plus 2x plus 1, and the original function is multiplied. The term x squared plus 2x plus 1 can be written as x plus 1 squared times e to the power of 1/3 x cubed plus x squared plus x minus 1. We require this to be 0. So this reduces down to x plus 1 squared must equal 0. So we have x must equal minus 1. This is where the stationary point occurs. Show that the function y equals e power 2x satisfies the equation second derivative of y minus first derivative of y minus twice y equals 0. Let's have a look at this one. Writing out the equation that needs to be satisfied and then substituting in what the y is. So that is the second derivative of e power 2x minus the first derivative of e power 2x minus twice e power 2x equals 0. So we have to do the derivative twice on e2x, find the derivative once on e2x, and just leaving e2x alone for the last term. Differentiating once and I get 2e2x, but one derivative remains to be calculated. And then doing the derivative once, 2e2x, and then the function at the end stays the same. Now we do the derivative again, differentiating again, and I get 4e2x since another 2 comes down, and then the rest of the equation stays the same, minus 2e2x minus 2e2x. So in total we get 0e2x since we have 4e2x minus 2e2x minus 2e2x. So we have shown that the equation holds. Here's one I would like you to try. Show that the function y equals c e power ax satisfies the equation dy dx equals ay for a real non-zero constant a. Pause the video, try this question, and when you're ready, resume to see the answer. We have dy dx equals ay. So we need to show that the derivative of c e power ax equals ay, which in this case would be ac e power ax. For e, to find derivative, we just take the derivative of the power, which in this case will be a, and that just comes down in front. So, differentiating, we have ac eax equals ac eax. QED. Here's another one I would like you to try. What is the derivative of 2 power x? My advice for this question is that you need to write it in the form of e power something, since we know what the derivative of the exponential function is. Pause the video, try this question, and resume when you're ready to see the answer. We have y equals 2 power x. I'll take the log of both sides, so now I have log y equals log 2 power x. But we remember that for log we can take powers down in front, so we have log y equals x log 2. Now, we take the exponential of both sides. E and log on the left cancel, and I'm just left with y. And on the right I have e power x log 2, which I'll write as y equals e power log 2 in brackets times x, to emphasize the fact that log 2 is a constant multiplying the x. That is, log 2 is a coefficient of x. Finding the derivative is not so difficult now, since it's like a problem e power kx. The derivative of kx is just k, and it's not much different here. E power log 2 times x is of the same form. The log 2 is just a constant and can come down. So we have y derivative equals log 2 ex.